Hello, 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 hello. Don't know how many people are watching, but apparently I've got 2 likes already. Don't like yet. You might you might find it less fun. Cool. Who's here? Nick is here. Hello, hello, Nick. Good. Right. So in the previous, and hello, Ollie, as well. In the previous catch-up streams, we looked at converting between the various different numbering systems: binary to hexadecimal, hexadecimal to binary, and denary, and all of that. But it was all very much a sort of here's a thing which I'm going to tell you about, and good luck finding a practical use for that. So what we're going to have a look at today is actually why binary is actually useful inside computer systems, and actually how the data is stored on a computer system in a manner that can be read by the CPU. So that's what we've got in store. Obviously, don't swap seats with the person next to you, because they might get a little bit confused. We're not gonna do all this. This is all practice that you can do. I mean, obviously on the rerun, you can pause the video here, and you can follow those instructions if you want to, for a little bit of extra practice. Okay, so the objectives here: understand how binary is used within computers. So we looked at why binary is used within computers, because it's the only thing that the computers understand. But we're going to have a look at the specifics of how it is used. It's all well and good saying computers only understand binary, but we need to actually know how they make use of that binary in order to store data. We'll look at something called a character set, and we will have a look at encoding and decoding images and text using binary, and I'll show you as well how that sort of like relates to hexadecimal as well, because binary numbers tend to be fairly difficult to look at, whereas hexadecimal numbers are a lot nicer. If there's time, we might be able to have a look at sort of the concept of hacking video games. And when I say hacking video games, I don't mean like hacking live online games in order to cheat. What I mean is like editing your video game save games so that you can adjust the amount of money that you have saved in there. If I had more preparation time, I'd give you a working example of that, and maybe I'll produce a separate video showing the process there. So that's what we are going to be having a look at throughout the course of this. If there's time, we'll look at digital audio, although we'll see how it goes. So just remind me and remind yourselves why is binary the language of computers? What's the deal there? Why is binary the only language a computer can understand? And what the hell is this thing? Why have I got a picture of that weird thing on my screen? Give me some answers. Answer me. That thing definitely is a transistor. This transistor is way larger than the transistors which are inside the CPU. We're going to have a look at a video in a second that gives you a greater idea of the scale of things. What is a transistor? What does it do? What's the point of that, and how does that relate to binary? Furiously typing away there. I can see you typing away. Give me the short version. Oh my. This is going to be a big message. Hit enter. Show me what you've got. Right, so binary doesn't actually measure the electrical signals, but the binary signals are right. A transistor is essentially a switch. It can be either on or off, kind of like an electronic valve in a way. So they're either on or they're off, and the combination of them together, either being on or off, determines how data is processed, added together and stuff like that. Multiple transistors go together to form logic gates and not gates, and out of those logic gates we can construct things like adders and multiplexers and all sorts of other internal workings. In fact, the memory inside your computer is made up of lots of transistors all linked together, right? And so because these switches can be either on or off, that corresponds to either a 1 or a 0, right? We're effectively sending little bits of electricity around our computer. In theory, it would be possible to build a steam-powered computer which would do the same thing, probably less efficient than an electronic one, but the same principles hold there. Okay, so these switches are either on or off. They activate the logic circuits within the computer, and they can only be on or off. There is no in between. It's either on or it's off. Once the electrical signal crosses a threshold, the switch turns on, and so that is why computers only understand binary. I've got a little video here. I will put credit here. Let me copy the link. I hope it's all right for me to show this video inside my video here. So I'll put a link in the description or something like this. But this is like a zoom in to a microchip, and bear in mind this is an old microchip, so it's not as micro manufactured as current chips, but still. So I'm just going to pause the video here. Ignore those thumbnails, don't know what that is. I'm just going to pause the video here. So this chip is maybe about I don't know, a couple of centimeters across, perhaps, and a centimeter tall. The actual processor bit of it is this bit in the middle. Okay, all of the other bits that are around the outside, those are actually wires that connect all of the inputs to this system to the pins on the outside of the chip. Okay, so we'll keep on zooming in here. Looks like Tommy's crashing the party here, blissfully ignorant of what's going on. So obviously we're zooming in, We had to change the cameras here. It does get a little bit faster as well shortly. But this bit in the middle is about about a centimeter or maybe 5 millimeters across. Very, very small, the actual bit of the CPU that does the processing. Okay. So we now continue to zoom in. We keep on zooming in, and now you can really see those individual wires which are connected to the pins around the outside of the CPU. Now we're going to have to get even smaller now. We're going to have to change our equipment because we're getting to the point where zooming in optically isn't really going to help us out much. So we've switched over now to a scanning electron microscope. That whole section there is 1 millimeter. That gives you an idea of the sense of scale that we're dealing with even now, right? You can see there's multiple these little wires coming out, even in the space of 1 millimeter. There's 1, 2, 3, 4, 5, 6, 7, 8, at least 8, probably more like 10 of these tiny wires that are coming out just within a millimeter. But on that scale, these things look fairly huge, but we're nowhere near zoomed all the way in, so we're going to keep on going now. Bear in mind, this is so small you will not be able to see it even with a powerful camera. The electron microscope is the thing that's going to help you see what's going on. So we're getting bigger and bigger and bigger. 60 microns. That distance there is 60 microns. Okay, a micron is a thousandth of a millimeter. Pretty damn small. Okay, so that's 60,000th of a millimeter there. But we're still not done. We're going closer and closer. You can see we've got this sort of like crisscross pattern of these. These are sort of the conductors that link the various different sections of the CPU together. It's incredibly complex, and there's lots and lots and lots of them all crossing over. So you can see that these ones pass over. They don't intersect. We are now down to 6 microns. So each one of these like connecting lines is a couple of microns thick, which is very, very tiny. We're talking thousandths of a millimeter, but we're still not done. We're going to keep on zooming in. We keep on zooming in, and now remember these things are like a couple of microns across, and so we have here. 1 micron, that's 1,000 nanometers. 1,000 nanometers, very, very small. And as I said, this is an old processor. So modern processors go even smaller than this, right? And there's a little bit of artistic license used in the video in a second. We're still talking like 1,000 nanometers here, right? And inside there, this is obviously an artist's rendition. This is not actually the picture. This is just to give you an indication here. So in that 1 micron space, you've got each of these tiny little dots is a transistor. Okay, so they are what, 20 nanometers. So there's going to be 50 by 50. That's what, 2,500 transistors just in the space of like 1 micron. And as I said, modern computers even smaller. You can get even more of these transistors. So 20 nanometer transistors, you can go even smaller now. Okay, so that gives you an idea of just how many of these transistors are in the CPU. Because bear in mind, we zoomed all the way in. There are billions of these things inside your CPU, and the way that they're all connected together is what allows the CPU to process information in binary format. Okay, so there you go. You heard it here first. Nanotechnology creates smaller, better computer chips. How do I now go back to my presentation here? Let's go back and forward. And forward again. There we go. That gives you an idea of just how many of these things there are inside the CPU. We're talking billions of transistors, billions of tiny little switches that are turning on and off billions of times per second. It's really, really quite extraordinary. Is there a physical change in the storage of a computer when new info is stored? The transistors are they form your memory. If we're talking about RAM, the physical change is it's all to do with like the electrons. The transistors are semiconductors, right? And so there is a physical change in the sense that the transistors are flowing from one. The electrons are flowing from one part of the transistor to the other, but it's not like a mechanical change, if that makes sense. It's fairly complicated, especially for non-volatile storage. Wikipedia has a fairly extensive article about NAND flash. If you want to read about how your USB sticks like store information, how do transistors physically work? They use a kind of similar to diodes. They are semiconductors. The actual way that they work, I'm not going to get into now because I could have like a whole video on those, and it's not necessary for the GCSE for you to know that, but if you're interested I can point you in the right direction of how these things work. So it is pretty interesting. Okay, so Transistors, boom. Now you know what transistors are, sort of, and kind of what they do, right? And the fact that there's so many of them inside the CPU, that is why we use binary. So obviously, binary is great for computers. They've got billions of transistors inside them. They understand how the combination of those transistors being on or off relates to the information that they need to use. Well, I mean, in theory, they don't really understand it. They just do what they do because they're inert machines. What are they built of? Silicon. I think mostly silicon these days. But yeah, semiconductors, silicon or germanium. Don't think they make them out of germanium. So binary is great for computers. It's not much use for us because it's difficult for us to understand 10001111101010110011, and it's even more difficult for us to say it. Okay, we need more than just 1 and 0. We need much more than just 1 and 0. Okay. Question, which for some reason everyone always seems to get wrong. How many letters are there in the alphabet? How many letters are there in the alphabet? 26, yes, boom. 26 letters in the alphabet. Not 25, not 27. 29 is right out. If we number those letters, A equals 0, B equals 1, C equals 2, D equals 3, etc., 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 how many bits would we need to represent all of them? Right, so what I'm essentially saying is the highest value that we can represent is going to be 25 if we're starting from 0. Right, 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up there. What is the minimum number of bits that we would need to store that many characters? What's the minimum number of bits you'd need to store the value 25? Not 4. With 4 bits, the maximum value you can store is 15, right? 1111 is 8 plus 4 plus 2 plus 1, which is 15. And so with that knowledge, yeah, 5. If we had 5 bits, we would need we would have a total number of we'd have 32 different values. You know, we go all the way up to 31, and then with 0 as well. Okay, but that's just the letters in the alphabet, right? What about other symbols, right? What about capital letters as well as lowercase? Okay, so if we're talking about the difference between capital letters and lowercase letters, uppercase and lowercase, that instantly doubles the size of our data set. So we've gone from 26 to 52, and then we've got all of these other symbols. I mean, you can have a look on your keyboard, have a look at how many symbols there are. Also, we've got digits as well, 0 to 9. How many different characters do you think there are in total, as a rough estimate? Based on what you can see on your keyboard, how many of them do you think there are? 367. 367. That's a lot. Where's that come from? So we've got the 52 letters. And then we've got 0 to 9, that's 62. We've got all the symbols on this. Total guess, yeah, that's fine. So if we work through this logically, we've got 52 letters for uppercase and lowercase. We've got the digits 0 to 9, which takes it up to 62. We've also got all of the symbols above each of those letters. That takes it up to 72. We've also got the brackets here and the plus and minus. So that's another 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters. So that's taken it up to 82. Then we've got the additional characters. So we're up to about 92. Yes, so around 100, 110-ish. And those are just the ones that are on the keyboard. Okay, So if we assume a conservative estimate of 110, how many bits do we now need to store all of those characters? So if we're going up to 110 of them, what's the minimum number of bits that we would need? I'll give you a clue. Yeah, I was going to say you can double it each time, but you're absolutely right, Ollie. 7 bits. What's the total? What's the highest value? Sorry, what's the highest value that you can represent with 7 bits? Yeah, highest value you can represent with 7 bits is 127. Okay, so we've got 128 different possible characters, and we only need about 110 of them. So we've got room to spare, which is nice. Okay, so there is this thing called the American Standard Code for Information Interchange. There are 128 different characters. Not all of them are printable. Remember I said we had room to spare? Some characters are not actually printable characters that will appear on the screen, but they're more things that are used like control codes and stuff like that. You know when you hit the enter key and it creates a new line? Well, what that actually does is it inserts the carriage return character. You know in Python where you type \n, right? That \n, that's actually mapped to a character in the ASCII character set. Okay, it's obviously \n is 2 characters, but that's because there is no way of entering that character that we need to use. Okay, so we have a list of every single character that can be printed or not printed as it is, and every single one of them has a specific and unique number. As an example, capital A is 65. Okay, if capital A is 65, what is capital Z? Not 89. Not 89 because A is 65. If you subtract 65 from that, you get 0. If you go all the way up to Z, that would be 25. So if you add 65 to 25, you get... You're very close. Both of you are very close. Yeah, it's 90. 90 is capital Z. Sorry, I'm just typing a message here. Right, so in theory, using that knowledge, you can spell out your own name, right? But this right here, hopefully you can see that okay. This here is the full ASCII table. Okay, the values. This one, the values for each character are listed in decimal, in hexadecimal, and in octal as well. Does anyone know what octal is, or does anyone have a guess what octal is? Base of 8. Yes, it's base 8. Okay, octal is base 8. Now, obviously, for the purposes of this, you don't need to... I just completely messed something up. You don't need to know hexadecimal or octal values. You don't even need to know the ASCII values specifically. You just need to know how this is made up. But interestingly, the first 32 characters, so from 0 all the way up to 31, are not actually printable characters. Look, item 0 is null. There's nothing there. Right, we have these other ones as well. A lot of these are sort of like hangovers from the days of telegraphs and stuff like that. So we've got things like start of text, end of transmission. My favorite here, bell. That will make your computer beep. It's not always properly interpreted these days, but still. So the first 32 are not printable characters. But then we start off with space. Okay, space is character 32, and then we've got a whole bunch of symbols. We've got a whole bunch of numbers here. Now, here's a question for you. What do you notice about the order that the symbols are in and the order that the numbers, the digits, are in there? Do you notice anything about that? Is it? Are there any sort of conclusions you can draw there? Are there any similarities? Bearing in mind, it's the American Standard Code for Information Exchange. Yeah, so obviously if we're using a UK keyboard, the layout is slightly different to this, okay? But still, Shift and 1 will get you the exclamation mark. Shift and 2 will get you the quote marks. Shift and 3 on a American keyboard will get you the hash symbol. They call that pound. Interesting. Shift and 4 will give you the dollar sign. Shift and 5 will give you the percentage sign. Now, interestingly, here we have the circumflex or the caret symbol on 6. They have the ampersand. Our ampersand is over 7. Now, I don't know whether that's different on US keyboards, but anyway, same sort of deal applies here. We've got the A, B, C, D, E, F, G. So we can see that A is 65, Z is 90. Here's a question for you. Yeah, okay, that's fair enough, Nick. That's fair enough. Just out of interest, is there a South African standard, or is it just use the American one? Or is there a specific South African one? I don't know. Just use the American one. Okay, that's fine. What do you notice here? Look, we've got all these numbers down here. Why do you think that it doesn't immediately go from capital Z to lowercase a and across? I mean, it's fairly easy to see from the layout of this table, but why do you think that's the case? Because of all the janky symbols on the right side of the keyboard, it's actually there's something else to it. You're kind of right. I mean, you've got all these symbols here that you can see. They are kind of like the ones on the right hand side of the keyboard, but at the same time, that's not the real reason. It might help if I bring up GIMP and give you an idea here. So. If we have a look here, as I said, capital A is 65, right? Lowercase a is 97, right? Remember those numbers, 65, 97. Okay, so I'm going to pull up GIMP. Let's turn it on. Boom. Okay, so we've got capital A is 65. Lowercase a is 97, okay? If we convert these numbers to binary, let's do that now. Convert these numbers to binary. We said we were using 7 bits, so we might as well carry on using 7 bits. So first, if we were to write the magic numbers, we would have 1, 2, that's a 2, 4, 8, 16, sorry, 32, 64. Okay, there's our 7 bits. 65 isn't going to fit in 7 bits. Are you sure about that? Because 65 is greater than 64, so we're going to put a 1 down there. Yeah, we subtract 64 from 65 and we get 1 left. So now 32 is greater than 1, 16 is greater than 1, 8 is greater than 1, 4 is greater than 1, 2 is greater than 1, 1 is equal to 1, so we put a 1 in there and then subtract 1 and we're left with 0. So yeah, you can't hide your shame, Tommy. I saw it there. Okay, don't tell the octal joke you always tell. What's the octal joke? Oh, yeah. Classic joke. I won't tell it unless anyone requests for it. The hilarious joke about octal. So that is 65. Okay, we're agreed this here, 65. Yeah? So Nick hasn't heard it. So the joke is, why don't number-based jokes work in octal? Look, I think it's funny. The reason number-based jokes don't work in octal is because 7, 10, 11 Oh, good. I love it because not only is it like it requires knowledge of another crap joke. It requires knowledge of computer science. And also, every time I tell it, Tommy gets annoyed. So, so there's that. Yeah, why is 6 scared of 7? Because 7 ain't 9. Is the joke that it's sort of based off, and in octal 8 is 1 0 and 9 is 1 1. So why don't number jokes work in octal? Because 7, 10, 11. Anyway, we got off topic a little bit here. So if we now convert 97, we can write our magic numbers out again here. We've got 64, 32. I feel like I've swallowed a live bee. 16, 8, 4, 2, 1. He thrives from the pain that comes from telling that joke. Yeah, you know it's true. So if we convert 97, what do we end up with? We have 97 is greater than 64, so we're going to put a 1 down there. If we now subtract 64 from 97, we end up with 33, right? So we're going to put a 1 here, and then we subtract 32 from 33, and we end up with 1. So all of these now are going to be 0, except for that last one, which is going to be 1. Okay, so we have uppercase A is 65, lowercase a is 97. What do you notice about the binary representation of those two numbers? Do you notice anything about them? There's another one. Yeah, it's literally exactly the same, except for this bit here is 1 there and it's 0 there. And it's the same for any of the numbers. If I increase this by 1, so 66, for instance, which would be B, is going to be 1 0 0 0 0 1 0, right? If I just delete this working out here. And if I add 1 to this, so 98, which would be lowercase b, it's going to be 1 1 0 0 0 1 0. It's the same number, but this bit here is either 1 or 0, right? All we have done is turn this bit on or off, right? And every time when you hit the shift key, what it's actually doing is it's turning that bit on. Okay, or off. Yeah? Anytime you convert something from lowercase to uppercase or uppercase to lowercase, all it's doing is turning that bit on or off. The upper command in Python or the lower command in Python, literally all it does is look at the binary and change that bit. That's all it does. That's all it needs to do. Okay, does that make sense? Why it's laid out like that? You see, Tommy? People do like that joke. People do like that joke. Right, okay. So let me just turn the old Gimperoonie off again. Now, obviously, although this is a good system, it's there are some limitations. What potential limitation? Oh, here's the ASCII code like converted to binary. Makes it a bit easier to see. Now, by the way, obviously there are 8 bits in each of these. There is a reason for that. You can see that every single one starts with 0. This is leading me on to the next point that I'm going to make. What is the what are some of the drawbacks of this, do you think? Can you think of anything that's potentially bad about this? We've got what, 90 odd symbols here. What's the problem that we might run into if we're using 7 bits to represent all of these characters? It's not slower necessarily. There is an issue. Yeah, there is a limited amount of characters you can have. And this is something, again, I don't know if in South Africa there are sort of like special characters. I'm guessing not. I don't know whether there's like Afrikaans has any special characters like we have in German and Swedish and French. Yeah, so obviously over here we have other characters that might be required. E with the accent above it. E with the accent above it going the other way. You know, O umlaut, U umlaut. Obviously, there's no space for them in the standard ASCII set. And so there is something called the extended ASCII set. The extended ASCII set basically increases the number of bits used by 1. So instead of 7 bits, it's 8 bits. What effect does that have on the number of characters that can be stored? If I increase the number of bits used by 1, what effect does that have on the number of different characters that can be stored? Or how many different characters can be stored if we have 8 bits? Yeah, it doubles the number of characters available. Now, obviously, we still have these characters reserved for this, right? But having the extra, we effectively add 4 more columns to this table, and with extended ASCII, it's very useful for having foreign characters. Now, there are some languages that have even more characters than that. If we're talking about things like Chinese, Mandarin, Cantonese, Japanese has 3 different alphabets, one of which is not a single symbol per sound, it's a single symbol per word, and there's something like 30,000 or more kanji. Obviously, even 8 bits is not going to be enough. And so there is something called Unicode, which doesn't quite follow the same sort of process as ASCII. I'm not going to get into the ins and outs of how it works, but there is a really good video which I will stick up on the Google Classroom for you if you're interested in how Unicode works. The first 128 characters of Unicode map exactly onto the ASCII character set, and what it does is it uses it uses a variable number of bits depending on what how you've got it set up. Again, I can give you some ins and outs of how that works, but basically what you need to know in terms of this is like a character set obviously has unique numbers representing each individual character in there. Therefore, the more bits used to store those unique values, the more characters you can store. And so if you need to store special symbols and things like that, you will not be able to with the standard ASCII, which only uses 7 bits and has 128 different characters. But if you use extended ASCII, which has 8 bits and can store 256 different characters, it gives you a lot more capacity for those different characters. And if you use Unicode, it gives access to thousands of different symbols that you can use. The other thing to bear in mind is that the computer needs to know what character set you are using, because the data is just stored in binary format. And that's why when we create web pages, we have something along the lines of a meta tag which says what type of encoding we use. Like if we use 8 bits, well, okay, so Unicode is not strictly 8 bits. There's something kind of special to it. What do I think of chemical computers? I'm not entirely sure what you mean by chemical computers. You have to give me some more deets there. Right, I'll take the Unicode thing offline. I'll do it. I'll give, if you speak to me tomorrow, Ollie, I'll give you an explanation of how Unicode actually works. Right, but it has a number of different sets of sort of like bytes. But anyway, I'm getting sort of off topic. So the more, basically, the long and short of it is the more bits you have, the more characters can be represented. Okay, that's basically it. As long as you can remember that individual characters have their own unique code. Every single character has a unique code, right? And when we store things in binary, have I got an example here? When we store things in binary, what we do is we convert these codes to whatever character is mapped against it in the ASCII table. We can do a quick example. Let's do a quick example. So, for instance, if I wanted to encode, let's encode. Someone give me a word, a short word. Give me a short word. Monkey. Okay, not amazingly short, but it'll do. Monkey. I'm just going to use lowercase. Okay, so what we do is we look up. You get what you're given. All right, I see how it's going to go. We look up each of the letters in the ASCII character set. So we've got monkey. So first of all is a lowercase m. That is 109. Okay, so m is 109. Convert that to binary and we get, if we're using, I will use the full 8 bits for this. Okay, we get 0, 1, 1, 0, 1, 1, 0, 1. There's our first letter. The O. The O is, what's that? O is 111. Okay, convert that to binary and we get 0, 1, 1, 0, 1, 1, 1, 1. Okay, and so on and so forth, right? That N is 110. Convert 110 to binary and we get 0, 1, 1, 0, 1, 1, 1, 0. We've got a K now. That K is 107. Convert 107 to binary and we get 0, 1, 1, 0, 1, 0, 1, 1. We've got an E. E is 101. Convert 101 to binary and we get 0, 1, 1, 0, 1, 0, 1. And then finally, we've got a y, which is 121. Right, and if we convert 121 to binary, we get 0, 1, 1, 1, 1, 0, 0, 1. So monkey converted to binary, for the benefit of Tommy, is 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1. Okay? I'm not going to do that word. I'm not going to do that word. I'm also not going to do anti-disestablishmentarianism or hippopotamonstrosesquipedaliophobia or anything like that. Don't pretend you didn't enjoy reading all those numbers out. And then obviously, if we were converting back, we'd split it into 8-bit segments. So here's the 1, 2, 3, 4, 5, 6, 7, 8. There's our first letter. Here's our second letter. 1, 2, 3, 4, 5, 6, 7, 8. Here's our third letter. 1, 2, 3, 4, 5, 6, 7, 8. Here's our fourth letter. Here's our fifth letter. And here's our sixth letter. And all we would do is convert those binary numbers back to denary and look them up in the ASCII table to find out where they are. Okay. Now, obviously, if you are using a different character set, the letter M might not be the letter associated with the number 109. So if I had this binary data and I was using a different character set, I might not get the word monkey. Normally, the standard letters will map to the same locations, but you may have been browsing the internet and come across a website, and on the website you'll see various characters that maybe look like this, like a little diamond with a question mark in, or maybe you've just got loads of boxes, some empty squares like that. Okay, that will be parts of the web page where the text has been encoded using some character set which you are not actually using. Okay. You're 7 bits, Tommy. Don't make me fight you. Yeah, I missed out a 0. There should be another 0 in there. All right, nobody's perfect. Monji. Actually, it probably wouldn't translate to Monji, because what you'd end up with 0, 1, 1, 0, 1, 0, 1, 0. Yeah, which is, but then you'd start from 1, 1, 1, 1, which is not actually a character. So you'd get monge and then some random character. Monk. Yeah. Anyway, but the principle is sound, right? You understand what's going on there. I could in theory give you a bunch of binary and you'd be able to convert it back to text. Okay. In fact, you can write a computer program that will do that. If I had time, I'd get into it now, but I don't really have time to do that. Maybe I'll do a separate. Maybe I'll do a separate stream. There's some nonsense going on in the chat there. Don't call me monkey. Yes. Cool. Right. We're not going to do that. We're not going to do that either. We are going to have a look at images, because the way that images are stored is actually very similar to the way that text is stored. If you can imagine colours as letters, it's practically the same thing. Are we going to do this in 2 months-ish? Yeah, I don't know. Maybe. We'll see how it goes. I might have to ramp it up a bit and do a few more per week. Okay. So the simple way of putting this is each computer image, right, is made up of hundreds of these blocks called pixels. You've probably heard the term pixel before, right? A pixel is a single block of color in an image, right? Each pixel can only be one color. You can't have multicolored pixels. right? They are a solid single color, kind of similar to cross stitch. I've got my little Charmander cross stitch on here. So each cross is a single color, okay? And the way that it's made up, I mean, pixel art images make great cross stitches, I think, if you're into that sort of thing. Yeah. So if we break it down, so we've only got a couple of different colors, i.e. dark green and light green here, we can map those colors to either a 1 or a 0. You know, it's either this color or it's this color. Yeah, and each pixel in the image is either effectively on or off, right? This would be kind of similar to only having two different letters, 1 or 0. Yeah. So in this row, if we're mapping like dark green to 1 and light green to 0, we have 1, 1, 0, 1, 1. In the next row, we have 1, 0, 1, 0, 1. In the next row, 1, 0, 1, 0, 1. In the next row, 1, 0, 0, 0, 1. And then in the last row, 1, 0, 1, 0, 1. I've written them at the side here. To show how the individual rows would look, but the actual image itself, it's just a long stream of binary like you see at the bottom there. Okay, so that's not all that's stored in the image. There will also be some information about what type of image it is and also what the dimensions of the image are, right? But it's not stored in neat like rows and columns like the actual image. It basically at the start it will say, oh yeah, this image is 100 pixels wide or something like that. In this instance, we're saying this image is 5 pixels wide. So the system knows once I have drawn 5 pixels, I drop down and do the next row. Okay, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. Does that make sense for like a 2-color image? Yeah. So if I have 1 bit per pixel, I can store 2 colors per pixel. Okay. The maximum number of colors I can have in my image is 2. Will you be asked to write a string of binary from an image like this in the exam? No, you will not. You'll be asked to explain, possibly giving examples. And so write in the binary from an image. That's sort of like you could use this as an example. Yeah. That what they often do is they will give you, to use a more like complex example here, they'll give you something like this color index, and they will say, explain how this process works using this as an example. Now, obviously, this is a low resolution image. I can't properly draw the Union flag here, but I made a good go of it. But this time, instead of using just 2 colors, we've now got 4 colors. Okay, and these 4 colors can be mapped against these different binary values. So 0, 0 is red, 0, 1 is blue, 1, 0 is black. Black doesn't appear on this. Nearly said something incredibly racist then. And there is a 1, 1 is white. Okay, so black doesn't appear in this particular image. So we've got each pixel will have 2. Yeah, I mean you can if you look at the binary as it's laid out there, you can almost see the flag. But bear in mind, Ollie, that the binary won't be in neat rows and columns like this. Okay, but the principle is exactly the same as it was in the previous one, right? You have 0, 0 for this first pixel. Remember, each pixel is represented by 2 bits. 0, 0. White is 1, 1. Yeah. Blue is 0, 1. Blue is 0, 1. White is 1, 1. So as we go through, we're still doing exactly the same thing. But instead of writing a single bit per pixel, we're writing 2 bits per pixel. So we get 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 0. Okay? Does that make sense what's going on there? Yeah? Do we see the difference between a single bit per pixel giving us 2 colors, 2 bits per pixel giving us 4 colors? I assume there's lots of dislikes on the video because there's people that don't understand computer science, or maybe, I don't know, maybe they're trying to annoy me by like disliking my stream. I assume it's some students. Haters gonna hate. I mean, if they've got nothing better to do in their lives than come on an educational stream and downvote it, you know, what can I say? They're probably already past the high point of their lives. But yeah, my content's awful. It's true. What can I say? But anyway, I'm getting off topic. So if we had 1 bit per pixel, we can display 2 colors, right? If we have 2 bits per pixel, we can display 4 colors. If I have 3 bits per pixel, how many different colors can I have in my image? 8, absolutely. Okay, add an extra bit and it doubles. Okay, so if, for instance, I wanted to have an image with 256 different colors, how many bits per pixel would I need? 8, absolutely. Okay, and 8-bit graphics were the standard for a large portion of the 90s before the PlayStation. I think the PlayStation was the first gaming system that used more than 256 colors on the screen at one time. I could be wrong. I think it used. I think it might have been 4,096 colors on the screen at the same time from a palette of 65,536. But I'm not sure. I hit like so you feel validated. Thanks, Tommy. I don't know where I'd be without you. I don't know. I don't know what I'd do. Yeah. What can I say? So many likes. I should set up a Patreon, shouldn't I, or an OnlyFans? Anyway, moving swiftly on. So yeah, I know, right? Sorry, I take it back. You get this concept, yeah? The idea that the more bits per pixel you have, the more colors can be stored per image. This is something known as color indexing. Not all images are actually stored like this. This is a color index bitmap system. Okay. The thing is, joke's on them, right? Because a downvote still counts as an interaction for the algorithm. So my video would be more likely to show up after they've downvoted than it would have been if they hadn't actually clicked anything at all. So, you played yourself. Okay, so... color indexing. This thing here is called the color index. And if you think about it, the way that this works is exactly the same as the way a character set works. Right? Remember, the number of bits per character determine how many individual characters you can have in your character set, right? The number of bits per pixel determine how many different colors you can have in your image. It's essentially the same thing, right? How you do your mum in binary code. Well, I mean, if you've been paying attention, you should be able to do that by now. So that's on you, my friend. If you don't know how to do that yet, then there might not be much hope for you, I'm afraid. Would a program identify whether something is image or text automatically? Not necessarily. However, different files have things called file type signatures. So at the start of the file, there'll be a set of bytes which are unique to the certain type of file. By Phyton, I assume you mean Python. Is Python or C better to begin? If it's your first programming language, I would recommend Python. It's a lot easier to sort of like get to grips with it out of the box, and it's a lot more easy to see where your errors are than in C. Anyway. So yeah, identifying whether something is an image or text. You can, in theory, open image files inside your... you can open image files from inside something like Notepad, and what you will see is just a wall of garbled text. Remember when we did... when we used Pickle to store binary information in Python, and when we opened the files, there was like a bunch of garbled text, right? That's because the binary information that it was storing, obviously it was just, if it was trying to interpret that as a text file, it would just look up each of those binary numbers in the character set and pull out whatever was in there. And that's why we ended up with a bunch of garbled nonsense. So yeah, you can open image files from text editors, and what it will do is it will split the things up into sections of 8 bits, and it will read them according to the character set, and you'll get a bunch of garbled nonsense. Is binary or English easier? Yeah, I'm not gonna answer that anymore. That's that. So I mentioned right at the start that binary is kind of difficult for people to sort of like understand, because it's a horrible wall of ones and zeros, and also each pixel will have multiple values associated with it in terms of the ones and zeros, right? It's a lot easier for people to see if that is converted to hexadecimal, right? And the reason we often, if we're viewing like the raw data of files, we would often use a hexadecimal editor, to view the raw binary data, but in a more human readable form, i.e. hexadecimal. The reason we use hex rather than denary is because of that direct mapping. You know, these 4 bits here, 0011, map directly onto this single digit 3. And this next one, 0101, maps directly onto that 5. Okay, so it's very clean in terms of mapping the binary onto the hex, whereas something like denary would be a bit more of a faff. Okay. So if you're dealing with hexadecimal, the chance of error, if you're inputting this into a system, for instance, the chance of error is greatly reduced, right? Because if I type in a 3, that's instantly entered those four bits accurately, right? But if I'm typing in the binary, I've got 4 chances of getting that wrong. Right, with the hexadecimal, I've got 1 chance of getting it wrong for like these four bits. Does that make sense? Yeah, cool. Okay. There is a thing on the there's a worksheet on the Google Classroom. Feel free to have a go at that. There's image conversions, text conversions on that worksheet. I was gonna wind it up because I've been on for about an hour. I don't know how you guys are off for time. If you wanted me to quickly go through the concept of hacking your video game save games so that you understand like the ins and outs of that without going into too much detail, I can do that, or I can just wind it up now. What would you rather? I can't stand your content any longer, so wrap it up. Okay, Tommy, thanks a lot. Thanks a lot. Well, I tell you what, this ain't going to take that long to explain. So it's only going to take about 5 minutes. All right. And also now that I know that I've made Tommy mad, so that makes me extraordinarily happy. Okay, so this is not about like hacking online video games in order to cheat or anything like that, right? What I'm talking about here is editing your save games so that you can change the state of your save game. Okay, talking about single player games locally stored, right? Anytime you save a game, the video game save games, they are basically just massive data files. Okay, they are stored in binary. You can view them in a hex editor, and you can see the hexadecimal values. Okay, now they will store things like what level you are on, what the current point in the level is, what your like coordinates are, if you like. If it's an RPG or something like that, they might also store your stats, so what your strength is, what armor you are currently equipped with, how much gold you have, and stuff like that. Okay, now normally, those save games files, they will store all of that information in the same position in the file every time. Okay, so maybe the amount of gold that you have is stored at address, I don't know, 0FF or something like that. Okay, every single time, that is where the amount of gold that you have is stored, right? So it follows, if we can find out what that place is, if we can find out what information is stored at what location in the save game, it means you can go and edit that information, and you can give yourself more stuff. Okay, bear with me a second here. There we go. So the way that we go about doing this is pretty simple. And as I said before, I will sort of like rush through this now and give you sort of like the whistle stop tour. And if you're interested, I can explain that. I don't know who that person was. They clearly someone with little or no life. But I don't know, maybe they'll get better or die. Who knows? So the way that this works is you load up your save game, right? You play your game for a little bit, and stuff happens, right? Maybe you pick up some gold coins, right? Maybe I've got, I don't know, 32 gold or something like that. I then save my game, yeah? I then save my game, and I look at how much gold I've got. If I've got like 32 gold, then what I will do is convert that 32 to hexadecimal. Okay, I now open my save game in a hex editor, and I search for the hexadecimal value for the amount of gold that I had, right? So if I convert 32 to hexadecimal, I get 20, right? So I'm going to open my save game, and I'm going to search for all of the instances of 20 inside the save game. Right, I make a note of all of the addresses where that 20 appears, and it's probably going to appear like quite a lot, right? So I make a note of all of those addresses, right? I then load the game back up, and I carry on playing, and maybe I do something that gets me some more gold, right? Now I've got 48 gold, for instance. I then save my game again. I open up my save game in a in a hex editor, and I search just the addresses that I had noted down before for the hex value of 48, right? So that's going to be what is that? 228 is that? No, whatever the value is. My brain's gone on the fritz, right? But you search, and what will happen is there will be some locations that stored that original 20 that you looked for, and there will be some locations that store it's 30, isn't it? And some locations that store that 30, right? And if the location that stored the 20 also stores that 20, it means you can narrow it down further, right? Then you go back into the game, right? You play it some more, you change the amount of gold, and eventually you'll get to the point where there is a single address that has the value of the amount of gold that you have. Once you've narrowed it down, you have found the address where the gold is stored, so now you can change that to FFFFFF or whatever, and give yourself tons of gold, right? To answer a question that Ollie asked, is this for older games? Does this still apply for modern games? It works in all of the older games. It still works in a lot of modern games, but it would depend on the save structure. It might be that the address where the stuff is stored is different. Depending on when the game was stored and stuff like that. You'll also find that more complicated games like Elder Scrolls games and stuff like that are storing ridiculous amounts of information, and so it might be more difficult for you to find that stuff. Okay, but it's still something that's possible to do. So you basically that's how you do it. You change the values, you work out what those values are, you get the list of the addresses where that information is stored, and then you go back, you change the data, you search just those addresses, and you keep on narrowing it down until you find a single address that stores the information, and then you can change it to whatever you want. Is it for online games? Right. So this is for local single player games that use a save file. This is not something that you can do on online games because all their data is stored on a server. It would also violate the terms of service if you try to do it for an online game. Okay, and bear in mind, it doesn't matter whether the game is running from a disk, from a cartridge, from your hard disk. This is only the save game data that we are editing here. Okay, so there will be a file with a save game. Okay, what I'll probably do at some point is I'll give a sort of walkthrough. I'll use DOSBox or something like that to create some hacked save files in like Dune 2 or Command and Conquer or something like that to show you how it works. Okay, so quick review here. I'm not going to ask the question, why do we use binary in computers? But how many characters can be represented using ASCII? The standard ASCII set. Standard ASCII, how many characters? More than 64. Remember, it uses 7 bits, standard ASCII. It said more than 64, Tommy. It's 128. Okay, it's 128 because remember, although the maximum value is 127, we still count 0. You know, that's still a thing. So okay. So what was the name of the 8-bit ASCII character set? What was that called? What's the name of the 8? There's a variant of the ASCII character set which uses 8 bits rather than 7 bits. Do you know what that's called? It's not octadecimal. Octadecimal would be a base 18 numbering system. It's not Unicode. It's not Unicode. Unicode is another character set. Unicode can store even more data than this one. So we've got ASCII is the 7-bit, 128 characters. It's not ASCII. It's although you're kind of close because you've done the thing. I'll give you a clue. Begins with E. There's 2 words. Second word is ASCII. First word begins with an E. Extended ASCII is correct, right? Extended ASCII uses 8 bits. Unicode uses a slightly different system and can store thousands of characters. Thousands. Okay, so three different character sets there. You are expected to know about ASCII. You are expected to know about Unicode, but not necessarily how it works. Just the fact that it can store more characters. Okay. Another question. Why do we sometimes use hexadecimal instead of binary? Yeah. Hex is easier to read because there's fewer. We can get more information in a smaller space. It's more dense information. Yeah, it's easier to read, and also if we're entering the data, there's less chance of an input error. Okay, because yes, one byte is 2 hex digits. Okay, one nibble is 1 hex digit. Remember, 4 bits to a hex digit. 8 bits will be 2 hex digits. And finally, how many colors can be represented with, well, we already know the answer, how many colors can be represented with 8 bits. So here's another one. How many colors can be represented with 16 bits? How many colors can be represented with 16 bits? Give you a clue, it's a big number. Way more than 32. Way more than 32. 16 bits? It's not a trick question. It's not a trick question. Yeah, 2 raised to the power of 16, which is what? I'll let you use a calculator for this one. Imagine using Windows Calc. What? Yeah, 65,536. Okay. Cool. We don't have enough time to go over audio, so that will be the focus of the next stream. Anyone got any questions before I call it a night? Could you find the hexadecimal for the name which stores your amount of money instead of the actual money value? What, you mean the name of the variable? No, that information would not be stored. Right, Tommy says his eyes are bleeding. This is I'm mostly asking Nick because this is his first time round. So are you all right, Nick? Are there any parts of that that you need me to go over again, or are we all good? Yeah, outstanding. Right, in which case, I will bid you adieu, and I'm going to go and paint some more stuff. Okay? Thank you, everybody.